Alright guys, so today we're going to talk about electrical components. So you've already used some of these in labs, but we're going to talk a little bit more about how they're used and the different ways that we can calculate their values so that we can use them correctly when we're building our circuits. So when talking about resistance, we've talked about atomic structures. So when we did that, we talked about that all matter can be considered electrical since it carries electrons. Um, the ones that are the most resistant carry between 5 and 8 electrons in their outermost shell, and the ones that are the really good conductors carry between 1 and 3. And then you have the class called semiconductors that carry 4. So we like the ones that run between 5 to 8 electrons in that outermost shell because those are the ones that are resistant to current. In other words, they don't like to give up their electrons. They like to hold on to them tightly and not let them go. So the whole principle of resistance is that it's an opposition to current. It's an opposition to the flow of current. The way we take advantage of this is that wire that is resistant will become hot when we pass current through it. So if you've ever seen a space heater that has if you've ever seen a big space heater and you have the band that goes to the floor, big base that's holding it on the floor, but inside you should see coils and coils of wire. And what this wire will do is whenever the heater is turned on, that wire gets red hot and throws off heat into the room to help heat the room. So this is what we use resistant wire with, and this is something we use very frequently. So what is happening when that happens is what's called dissipation. So this is heat that's produced through resistance and gives an energy conversion. So we go from basically almost kinetic energy to heat energy. So power dissipation is giving off heat, and the heat dissipation and power dissipation are equal to the power produced by your voltage source. So what your voltage pushes is the amount of power that this thing will allow it to work with. So what we're going to be learning now are about energy and power. So energy is a very basic fundamental capacity to do work, and it's measured in joules. So energy is what we're using that is creating work. It is the very basic fundamentals of all things. What we sell at the power company is basically how that energy is used. So the rate at which that energy is used is what we call power, and that's measured in watts. So anytime you've ever gone to buy a light bulb, you have to buy a certain wattage of light bulb so that it will work correctly with the fixture you're using and not overpower or underpower itself. We'll talk more about that in a minute. So power is equal to energy divided by time, or the best way I can say it is if you've ever seen a power bill, what you're paying by is what's called watt hours. Basically what this is how long were you using energy? In other words, your lamp, did you leave it on all day? Your dishwasher, how many times did you run it? All these things use energy. All of these things thus create work and use power and energy over time. And that is what the power company, Alabama Power, Tennessee, the Tennessee Power Company, those are the ones that tell you how much you used and how much they want you to pay every month for your power bill. So this is Watt's law. So Watt's law should look very familiar because it's a very close cousin of Ohm's law. So Ohm's law is V is equal to I times R, whereby V is the representative of voltage, I is equal to current, and R equals resistance. So we've started off with V, I, and R here. We're just adding one more element, and that is element P. P stands for power. So the way we're calculating P is we're using V and I. So we're going to use voltage and current multiplied together to get power. And just like with Watt's law, we used with Ohm's law, whereby if we had, let's say, voltage and we had our current, but we're looking for our resistance, we would divide voltage by our current. Well, in this case, if I'm looking for my current and I have my power and my voltage, I divide my power by my voltage. And then vice versa if I'm looking for voltage. So this looks and acts exactly like Ohm's law. We've just introduced power to it. So we use power over time. So you don't get a 75-watt light bulb and that's all you're using for, let's say, an hour. Most of the time we tend to put light on and we like to have light in our house. So how long that light bulb is used in the fixture and how long you leave it on, that's power consumption. Okay? So power used over time is in watt hours. You can literally go through different appliances, find out how much wattage they're using, and you can calculate your power bill by doing this. So let's say you look at a lamp and it's got a 50-watt light bulb. How long do you leave that lamp on daily? How long or how many days in the month have you left it on like that? And so thus you can start building up a picture of what you can do to save on your power bill, essentially. So in this case, they're telling you that you use 120 watts of power for 30 hours. By multiplying this out and putting it in engineering notation, you would then get 3.6 kilowatt hours. So if we go back to something like a lamp in your house, and you use that lamp to stay on all day when you're away. So we'll say it's a 50-watt lamp. Use a W to represent watts. And let's say we leave it on for 8 hours a day. And we do this 7 days a week. And the month is, well, let's just use February, whereby we have 28 days. Whereby we really don't need the 7 days because that goes into your 28. So what you'll do is 50 times 8 times 28. Okay? So 50 times 8 times 28. So when you multiply 50 times 8, you get 400. And then you multiply that by 28. When you multiply that by 28, you get 11 EET100, and converting that into engineering notation, you would get 11.2 kilowatt hours. So that's just for leaving a 50-watt light bulb on 8 hours a day, 28 days in the month. So why would this make a difference? Well, let's say you wanted to save on your power bill. This is a good way to calculate what in your house is using up and causing the biggest power use in your house. Certain things you wouldn't want to mess with, things like your refrigerator or your stovetop, but other things like TVs or your phone charger, things like that, actually use power even when nothing's plugged into them. It's a very interesting cycle how that runs. So in this way we can calculate that and we can find ways to save on your power bill. I've seen some people take it to the extreme whereby they start turning off circuit breakers in certain areas of their home before they leave, so that, again, you're just trying to save money on something as simple as a power bill. I wouldn't go to the full extreme whereby you kick off the main breaker in your house, because then you might come back to a really big mess after your refrigerator defrost, but it is a different way to see and maybe even take it to the next level. It's very interesting to use it this way, as well as if you're going shopping for certain appliances. Since most appliances will have on them somewhere how many kilowatts they use when they run. You can use that to help you determine what exactly you're wanting to get and how much it's going to cost you to run it. Just some different ways you can look at things as you go. So we've actually played with resistors a little bit in lab, and the way we have to look at resistors is in their power rating, okay? And this power rating is their guaranteed amount of power that it can use without damage. So in other words, a 50-watt light bulb, we'll go back to that real quick. A 50-watt light bulb, if you put it in a 120-watt socket, it will blow that light bulb every time. The light bulb cannot withstand the use of a higher wattage when it's such a low wattage itself. So you have to really consider what is the power rating of the object you're trying to put it, and what is the power rating of what you're putting it into. So the power rating is determined by physical characteristics. So they're determined by something that you are physically looking at, and that will help you figure out if it's okay to use. So these include things like length, how long is it, what is it made of, and how wide or how thick is it. And these will tell you exactly how much wattage it can handle. Sort of like bigger light bulbs handle bigger wattages, and they can also throw out more light that way. Whereas if you use a really small light bulb, those don't work as easily for that. And so we have a couple of different types of resistors, but all they do is limit current. That's all a resistor's job is to limit the amount of current that it is able to use or is able to pass. So if you remember back whenever we started talking about Ohm's law, we related it to a river. And on that river, we have a dam right here. All that dam is doing is it's holding back the current that's trying to come downstream so that it gets a lot less current on the other side, okay? The current can still pass through, but as it passes through, it's going to create work, because what is generally attached to these dams are power lines bringing power to us. So we're using those dams to create power. But the whole point of the resistor is to limit electric current. It's able to limit how fast that river moves through the dam. It's able to limit how fast the current is downstream. So we have two basic types of resistors. We have what are called fixed resistors. These are resistors that their value and their overall appearance won't change no matter what you do. These are a very fixed value, and we'll talk more about that in a second. But then we have what are called variable resistors. You see a picture of them right here down at the bottom. These are actually what are known as things like potentiometers and rheostats. The ones you see pictured are potentiometers. And these have a variable resistance. Another thing you might have heard them called is a variable speed. Oh Lord, it's a variable speed control, I believe. So yes, these use potentiometers to vary the speed of certain things. And these are if they're manual. If they're digital, they're using something else. But most resistors are made of carbon composite materials. They are made of metal film, or they are wire wound. Potentiometers tend to be between a couple of different ways, but the bigger ones are typically wire wound. Same with the bigger resistors. Those are the ones that are going to carry a lot more current. They might not have a high resistance value, but they're able to carry a higher wattage value because they're bigger. So these are some carbon composites. Again, these should look familiar. You've been using them in lab. Metal film chip resistors like these, all they are is they work on PC or printed circuit boards. You got your network resistor. You have them in single line versus an inline package. And then you have radial lead resistors. So you have a couple of types of fixed resistors. You have the carbon composite. Again, you should be very familiar with it. As a matter of fact, if you've ever opened the back of a circuit board, or the back of a TV, a back of a computer, you'll see a bunch of these. They all tend to be laid out all over the place. And you would also see a lot of these. And they tend to be soldered down onto the board. So you have color bands that we'll talk about in a minute, but the resistance material in the one with the leads are a carbon composition that carry an insulated coating to keep it from getting too hot and burning stuff around it. With the surface mount resistor, you have protective glass overcoats. These are your external electrodes, would be basically your leads. You have ceramic substrates, resistive material, and your internal electrodes with external electrodes still covering them. So again, these are typically soldered down onto a printed circuit board, and that is how, and you would generally see them, they're fairly small. They are generally a very small piece of equipment. So film resistors, if you have ones that are made of metal and they're this particular one, what they're showing you are a metal or carbon scribed helix. And again, you always have an insulated coating and you have it wrapped around an insulated base. The metal cap ends lead to your lead wires, which are going to move the current through it. But the long journey between these, which is where these white lines right here are, is what is creating the resistance, much like a old Edison bulb. And then you have a transistor network with the terminals that are your resistance. You have the resistance element right here that is keeping the current from jumping from one to the other faster than it would if it was just all metal. Your insulative coating, again, that's just to kind of keep the heat dampened down so it doesn't overheat other parts in your circuit board. And then these are some wire wound examples. Much like the ones here, which are film resistors, these are very similar. Again, these are just wire wound around a central resistive core with a resistive outer coating to keep it from overheating. But the current passes through each wire, over the wire itself, which allows it to move the current through, but the length of the wire that it's having to move through slows that current down. So it's kind of like if you put water into a hose. The longer the hose, the slower the water comes out at the other end until it's able to build enough pressure to go and faster. So for resistors, for the ones most commonly used and ones that are extremely common in electronics, we have a couple of different types. What they're showing you right here is a 4-band resistor, and it should look pretty familiar because we've used them in class. And here you have a color chart that tells you what this actually means, as well as a mnemonic to kind of remember it. So you have big, beautiful roses occupy your garden, but violets grow wild. Okay. So each color is correlated with a number. So you have black, which is 0, brown is 1, red 2, orange 3, so on and so forth. And you can find mnemonics everywhere online. So if big beautiful roses don't cut it for you, you find something else that you want to use, that's fine. But this is one of the more common ones that is fairly easy to remember. I've had some people tell me that the way they memorized it is they memorized the fact that this is all colors of the rainbow. And then you just have to remember that BB, black, brown, and then GW, gray, white. There's literally a million and one ways to memorize this, guys. So find your way and just kind of be ready to use it. So some of the additional colors, if it's in the multiplier band, so we'll talk about, so the multiplier band, second. So the way a 4-band resistor works is that you have a number, and this is something that's going to multiply. Followed by what's called a tolerance band. Sorry about my writing, guys. So what you would generally see, so in this case, you have brown, which is 1, black is 0, red is 2. So essentially what you would come down with this is 1, 0 times 10 to the 2, and then you have your tolerance band, which we'll talk about that in a minute. But essentially what this means is this is a 1 kilo ohm resistor. How do I know that? Well, because 10 times 10 to the 2 is 1,000. Okay. So you have your number and a number, then you multiply by the 3rd band, and your 4th band is the tolerance. Now, tolerance is an interesting word for this. Essentially what it means is that manufacturers have a window of correctness to use with this, guys. So for this particular one, tolerance is silver, which would be about a 10% ability. So that means that for this guy, he can be either as far down as a 990 or as high as a 110. No, I'm sorry. It's a, I'm a little off here. Sorry, guys. So you have actually got between 900 and 110. I'm sorry. I goofed my numbers here. 1,100 to 900. So that gives the manufacturer a little bit of wiggle room whenever dealing with this. So you have to know how much tolerance you have, because a lot of things are engineered with very low tolerances. Then you have to have a lower, have to have a stricter tolerance band. So in the multiplier band, we can have a couple of different colors, and those colors are gold and silver. Another way to write gold would be times 10 to the negative 1, and silver times 10 to the negative 2. It's a little bit easier than trying to multiply it by 0.1 and 0.01. And as for tolerance bands, these are common for these two are common for 4-band resistors. This is for a 3-band resistor. So the looser the tolerance, the more you have fluctuation between your numbers you're supposed to have and the numbers that you have when you actually measure the resistor. And then you have 5-band resistors, which have these tolerance bands. So red's 2%, brown is 1%. Okay. So red's 2%, brown's 1%, green is 0.5%, blue's 0.25%, and violet is 0.1%. Which violet means that it's going to be a very narrow gap between what you get and what you need for your tolerance. That means something's going to be very precise. Here's something you might want to memorize. So this is how a resistor works with its bands. If it's a 3-band resistor, you have your digit multiplier and then a 20% tolerance. We don't have to worry about this guy down here because it's only a 3-band resistor. You get 20% tolerance whenever you have no color. For that 3rd band. I'm sorry, for the 4th band, excuse me. For a 4-band resistor, again, you won't need column number 5 here, but you do have 2 digits, your multiplier, and a tolerance. Typically this is gold and silver, but some other ones like red or brown and some of those can be part of this. And then you have a 5-band resistor, which you have 3 digits before you come to your multiplier. So this right here is where you're going to have to make sure you are careful with these. is how many digits before you get to your multiplier. And then you also have to worry about where your tolerance band is. That tolerance band is always the last band. You will always have as minimum 2 digits in front of that multiplier before you come to your tolerance. So looking at this, just to kind of give you a little practice, what you should see here, and I know the color's not always very great with this, but this is a red. So let me kind of back up here. So you have black, brown, red, orange, yellow, green, blue, indigo or violet, depending upon who you go with or what color you go with. And then you have gray, white, and then for other colors you have gold, silver, and those are the ones that are secondary. I'll just put it at that. So this first one, if we're looking at BB, so we're looking at black, which is 0. And by the way, guys, let me go ahead and put this out there. A resistor will never start with the color black. And the whole reason for that is the fact that nobody starts their number out with 0. You don't say 0, 10 when you mean 10. Nobody does that. So you will never see a resistor start with the color black. Okay? And you'll also never see it start with gold or silver because these are strictly either multiplier or tolerance. So you will never see it start with black, gold, or silver, ever. Okay? If you're seeing it start with black, gold, or silver, then you're reading it the wrong way. You're trying to read it this way when you should be reading it that way. Generally, the way you can tell is that there is a gap at the end, but sometimes you just have to really pay attention and look at what you're doing. That's about all I can really say on this, guys. So just kind of really pay attention to what you're doing when you're working with these. So to color code this first one, red is 2, violet is 7, orange is 3, and then I have a silver band here, which is going to be my tolerance. And silver, like we said a minute ago, is plus or minus 10%. Okay? So when I start decoding this, I'll say 2, 7, and this, my third band is my multiplier, so that's times 10 to the third, and then plus or minus 10%. So let's break this down then. So first of all, if we put it in engineering notation, this is 27 kilo ohms plus or minus 10%. If I wanted to find my high value and low value for these, so let's say I've got one of these resistors, but I need to know if it's in tolerance. What I'll do is I'll take 27, and with 10%, the easiest way I can say to do this is take your decimal point you know is back here and move it forward one place. So what you'll do is you'll take 27,000 and then add and subtract 2,700. What you should get is 29 thousand or 2.9 or 29 kilo to 24.3. I'm sorry, it's not 29 kilo. It's I forgot my 7 there. All right, so it's 29.7 kilo. Forgot to move my 7 in there around and wrong. All right, so you have 29.7 kilo and 24.3 kilo. So if my range falls up to 30 kilo, that's bad. If it falls to 23 kilo or less, it's not a good resistor. It must fall in this range to be considered a good resistor. So moving to the next one. The colors here, we have brown, which is represented by a 1, black, which is a 0, brown is 1, and silver means we're doing a plus or minus 10% again. So essentially this is 10 times 10 to the 1, or it's going to end up being 100 ohms plus or minus 10%. So what this means is it's going to range between, so whenever I look to this to find the 10%, that means I'm going to be doing 100 plus or minus 10. So that means my range falls between 90 and 110. Okay? It'll fall as low as 90 and go as high as 110. So if it goes to 120, it's a bad resistor. If it goes to 80, it's a bad resistor. It has to fall between 90 and 110. Be considered within tolerance range. All right, then lastly, we have C, which is a green, which is 5, a blue, which is 6, another green, which is 5, and then we have gold, which is plus or minus 5%. So what this translates to is 56 times 10 to the 5th plus or minus 5%. Now the only problem I have with this is it's not in proper engineering notation. So in order to do that, bring my decimal, which is at the end of my 56, back 1, and I get 5.6 times 10 to the 6, which would be mega, plus or minus 5%. So then I need to find my range. So if you have your calculator, put in 5.6, or you can even type it all the way out, which would be, goes back to that when in doubt, write it out, guys. So 5, 6, 1, 2, 3, 4, 5. So you get 5,600,000. Either way, percentage you're going to add and subtract from your 5,600 you're going to add to and subtract 28,000. No, I'm sorry. It's 280,000. Excuse me, guys. Got lost in translation there. So you're going to add and subtract 280,000. So adding 2 is fairly easy. You should end up with 5,880,000. 5,880,000 or 5.88 mega. And when you subtract from, you should end up with 5,320,000 or 5.32 mega. Now, just to kind of show y'all an easier way that this can be done, is instead of dealing with all the zeros, is say 5.6 plus or minus 0.28. So 5.6 minus plus or minus 2.28. Because then you would end up with 5.88 and 5.32. Then all you would have to do is remember to bring down the fact that these are both mega. So you still end up with 5.88 and 5.32. If you feel comfortable doing that, that's great. If you want to write it out, that's fine. I'll leave the technique finding to y'all, but it's just a different way to look at it. Be a bit shorter of a way to do it so that you're not taking twice as long to do everything. The only thing you have to make sure you do is verify your numbers before you put them down. Okay. So just to verify our answers, there you go. So you have 27 kilo plus or minus 10%, and that leads you to a high of 29.7 and a low of 24.3. Looking at this guy, he's 100 ohms plus or minus 10%. That leaves you with 110 and 90. And then you have 5.6 mega plus or minus 5%, which is 588 and 532. So it looks like the answers we found just a minute ago are the ones we need. So looking at a 5-band resistor, so we've looked at 4-band resistors before. So with a 4-band, we have a number, multiplier, tolerance. For a 5-band, basically it's the same, only you have an extra digit in there. So you have a number, multiply, tolerance. So again, just to write this out for y'all, you have B, or black, brown, red, orange, yellow, green, blue, violet, gray, white. Okay. Then to look back, you have the other colors. So red is 2% wind intolerance. Brown is a 1% tolerance. And green is a 0.5 is a half of percent of tolerance. Okay. Just so y'all can kind of follow along here. So the very first thing you should do is identify your colors. So this guy is red. So that means he's a, excuse me. He's a red, so that means he's a 2. Violet, you go 0, 1, 2, 3, 4, 5, 6, 7. Black is 0. Yellow means 4. And here we come to our tolerance band, so that means we're going to do a plus or minus 2%. So translating this, we have a 2, a 7, a 0. We're multiplying by 10 to the 4th. And plus or minus 2%. So translating that into proper notation, so our decimals here, 5, 6, so we have 2.7 times 10 to the 6 plus or minus 2%, or 2.7 mega. Proper notation is key, guys. So 2% of your number here so if you just leave it as 2.7 and just have to remember bringing down your mega in a minute, you're going to add and subtract 0.054. So 2% of a tolerance is a lot smaller than the gold tolerance, which is 5%. In this case, we're using 2%, which leads us to 0.054. So when you add it to and subtract it from, adding 2, you'll see 2, 7, 5, 4, with your decimal right beside the 2 and the 7. Subtracting from, you get 2.646. Bring down your mega to both, and it's solved. And again, yes, you can very well go in and put in the last 3 zeros, should you want to. If that helps you, that's fine. Working with a shorter number to me just is a little bit easier of a time than having to work with a number that's longer. Because the longer the number, the longer it takes to solve. But again, that's just me. That's just a different way to do math. Okay, so then we come to our second one. We have yellow, which is 4. We have black, which is 0. Red is 2. Black is 0. And brown means plus or minus 1%. Oh dear. Translating to 402 times 10 to the 0 plus or minus 1%. 10 to the 0 basically translates to 1, so you have 402 times 1, which means you have 402 plus or minus 1%. So when you multiply 402 times 1% in your calculator, you should see you've got 402 plus and minus 4.02. A couple decimals behind that. Let me write my 2 here. Trying to make this as legible as I can for y'all. So adding it to, you should get 406.02 subtracting from, you should get 397.98. So that gives you the full range of this particular one. Not a very wide range when you compare it to the ones we did a few minutes ago on the 4-band resistors with 10% and 5% tolerances. These numbers are very narrow in how well they're spaced. This is the easiest way I can say that. The margin for error is a lot narrower. All right, so lastly, we come to our letter C over here. And we have orange, orange, red, orange, green. Orange is 3. So everywhere I see an orange, I'm just going to put a 3. And red is a 2. Last band is tolerance, which is green, which means I'm doing plus or minus 0.5%. So this will translate 332 times 10 to the 3rd plus or minus 0.5%. Put into engineering notation, this is 332 kilo plus or minus 0.5%. Now 332 times 0.5%. I said I'm just going to bring down my numbers, not mess with the zeros too much. But you are going to add and subtract when you multiply this in your calculator. So just to kind of give you an idea of what I'm multiplying in my calculator, guys, is all I'm saying is 332 times 0.5 This does not have a. And that didn't make do no good to. All right, so 332 times 0.005, which is 5%. So if you don't remember how to get a percentage, you should remember that 10% equals 0.1, 5% equals 0.05. So whenever you go to do 5% decimal form, that is 0.005. So what I'm adding to and subtracting from this is going to be 1.66. And again, yes, I could just do my commas here and put my third zero there and a zero there. It doesn't really matter, whichever way you're more comfortable with. But what you're adding to and subtracting from is you're adding, so you have your base number, 332,000, and you're adding and subtracting 1,660. So your added number will be 333,660. All I would really need to do is exchange my comma for a decimal. Subtracting from, you should end up with 330.34. Again, all you gotta do is bring down your kilo ohm, and you have your high and your low. Whichever way you choose to do it is up to y'all guys. But like I said, at the very end of the day, just remember, when in doubt, write it out, and it'll be a lot easier to work with some of these if you start finding yourself in utter confusion. Okay. All right, so this is 5-band resistors and how to decode them. Okay, 5-band resistors and how to decode. So looking at this, let's check our answers. So first one, we had 27. I think somebody forgot how to do this one, because that should be mega ohms. I'm surprised I've never seen that part before. It should be 2.7 mega ohms. I'm not sure how they, unless they're trying to call that a gold band. At the same time, we still got 2754, although ours was 2.754 and 2.646. I'll have to figure out what somebody was thinking with this one. I'm not sure if they meant yellow or gold. Anyway, so looking at this guy, we had 402. That is correct. So we ended up with 406.02 and 397.98. And then lastly, 332 kilo ohms plus or minus 0.5%. Give us 333.66 kilo and 330.34 kilo. So I would say our answers are correct. All right. So then talking about 3 digits, again, what you end up with is your digit multiplier, and then tolerance is 20%. That's all the difference on that. You just have a set tolerance, it's not going to change. So looking at these, you have 2 different types of variable resistors. One is what's called a potentiometer. The easier way to say that is basically a pot. You have what's called a potentiometer, short name is a pot. And then you have what's called a rheostat. Okay? The difference between the two, there's a couple of them. But the physical difference between the two is that a rheostat has 2 leads. In other words, this looks almost exactly like a basic resistor, whereby this guy has 3 leads. Okay? He's got 3 leads. You have the first lead, you have your third lead, and between the 2 of these leads is the entire resistance of the potentiometer, or pot. Then you have your second lead. Your second lead is where you will find variable resistance. Okay, so if you look between 1 and 2, you'll see a certain amount of the resistance, and look between 2 and 3. If you look between 2 and 3, you will find a certain amount of resistance. So the way you tell the difference between a potentiometer and a rheostat is that you have a variable resistance with 3 legs. Okay. Now the interesting about a potentiometer is you can connect it into becoming a rheostat. And you can do that by connecting leg 2 to either leg 1 or 3. And that way you would end up with a rheostat. So these are some very typical potentiometers. What you would generally find, again, is the 3 leads, and then you have some way to, like some sort of a type of screw or a type of dial that allows you to change the resistance on the inside of these potentiometers. And if you notice on these cutaway views, which is probably the most interesting view of this, guys, is the fact that you can see how these would move up and down, or just turning this around through the different parts of resistance. Again, these are kind of an interesting little resistor. So going between potentiometer and rheostat, and again, this is in your books, guys, so you might want to double check on all this, and it's very interesting. A potentiometer will have 3 terminals, a rheostat will have 2. Their composition is very similar. A potentiometer offers higher resistance and a rheostat not so much. Pots are usually smaller, rheostats are larger. Potentiometers control voltage. That's one of the bigger differences here, is that potentiometers control voltage. Rheostats control current. Okay, nothing else. You need to make sure you understand that and the difference in the terminals. They're both rated according to power, just like anything in resistance. They are always rated not just by their resistance, but by their power. All resistors are rated by resistance and power. Make sure y'all know that. It's a very big question. It's one that I frequently will ask on tests. Just kind of a heads up on that, guys. So make sure you know that all resistors are rated on their resistance and on their power. Okay. Now, a rheostat cannot be connected as a potentiometer. It only has 2 legs, 2 terminals. However, a potentiometer can be connected as a rheostat by tying 2 of its legs together, either 1 and 2 or 3 and 2. And the very short version of it is called a pot. Okay. And as a side note, in your book, now the books have changed over the last couple years. What this should read is 10.41, which is incorrect in your book. And that is where okay, so if you look at 10.41 in your book, the point where it's wrong is where it says that both devices have 3 terminals. That is incorrect. A rheostat only has 2. A rheostat only has 2 terminals. Okay? Which means that figure 11-8 is incorrect as well. They're calling that a rheostat. That's actually a potentiometer. I don't know where they're getting that that's a rheostat. Rheostats only have 2 terminals, guys. Okay. Because with a rheostat, what you would see isn't so much that it has a third leg, as that third leg and the one of the others is tied completely together. Just like when you turn a potentiometer to a rheostat. Okay. So other resistive devices, there's several out there. There's one specifically that relates to temperature that's called a thermistor. Um, these are used in heat applications of all sorts. Okay. It changes its resistance based on temperature. About the best way I can, and simplest way I can say that. And then you have what are called photoconductive cells. Excuse me. So photoconductive cells are ones that vary with their resistance with light. There's a couple of different applications for that. Um, one of the most common ones is with things as simple as a solar light, things that come on at night and turn off during the day. You can use something as like a photoconductive cell as their primary switch. So as the more light it gets, you can make it to where that shuts off the circuit. And then whenever it has very little light, it turns the circuit back on. Kind of a different way to do that. So we've kind of talked about this with the last chapter, but we have what's called conductance. As we talked about, this is the opposite of resistance. So if we go back to our river analogy, okay, we go back to the fact that we've got a dam across the river. Conductance is what, so you have to acknowledge the fact that, first of all, you can't push a river back entirely. You're going to have water that comes over or through the dam to allow the water to move downstream. The amount of water that is being let through would be your conductance. The amount of water that is being held back is your resistance. Okay? This is your conductance, this is your resistance. Your flow is your current. Okay? So this is the ability of material to allow current flow. So wire has a lot of conductance. Resistors don't. But we measure conductance in what are called Siemens or Mohs. Most commonly we call it Siemens. And that particular way we write that is just with a big S. And we kind of talked about this again, but the formula for this is that conductance is equal to, that your conductance is equal to the inverse of resistance, but the inverse of resistance is the inverse of your conductance is your resistance. The inverse of your resistance is your conductance. So if you've ever been to a hydroelectric dam across a river, you would see gates that are open and water pouring out. This would be your conductance. Okay? There's always water on the move here. This is your conductance. What water is being kept back here and building up behind this wall, that's your resistance. Okay? So what's being let through is your conductance, what's being held back is your resistance. That's why they are inverse of each other. They're inversed to each other. So one of the big things that's used in electricity and electronics are what are called capacitors. Basically, these are how to say this? They act almost like a 5-second battery or a 2-second battery. They don't hold on to a charge very long. They basically store and discharge the electrical charge very quickly. Okay. These work mainly with AC power. Another word you might have heard them called by is a condenser. But basically, when you put these guys in, they're going to charge and then they'll discharge. However, that can make them a little dangerous because if they overcharge or they get a short in themselves, they can cause some havoc. Kind of is what it is, kind of way a battery works. If you overcharge a battery, let's just say don't ever overcharge a battery. Things don't end well when that happens. So these guys charge and discharge electricity. Okay, that is their main function of existence, is charge and discharge. The way you can kind of think of this is this allows for, let's say if you're working on if you've ever looked at power lines, these are actually one of the big things they're putting in these days. They're all over the place. If you ever look at a substation, they've got a bunch of these. And what they do is they basically stabilize the AC power that moves through them, because they can take excessive charges. So for most part, we tend to think that there is nothing very wrong with AC. However, AC tends to look like this. It's not the regular up and down, up and down, up and down. It looks a lot like this. So what a capacitor allows it to do is look a little more uniform, because they will take excessive charge, because sometimes you get an excessive peak of charge. They'll take that and they'll hold on to it. And then whenever you get a particularly low dip, that's when they'll discharge. So basically, they are able to vary their opposition to the current depending upon the frequency and other things. That's pretty much their job, is just to kind of stabilize things and to provide a boost or take some of the extra whenever they're needed. It's an interesting thing about capacitors. Then you have what's called inductors. So inductors, let me say this first before I get into inductors, and that's that two inductors make a transformer. But this stores energy in electromagnetic fields. Again, they're also very opposition dependent on frequency on AC. So you won't really see this in DC, but you'll see it in AC. These are very, very commonly used in AC electronics. Then you have transformers. And these are used to increase or decrease AC voltages. So what you should know is that transformers, if you've seen them, they're generally outside on the street, and they have these three little things that poke up like so. Okay? And they will be connected in different ways. But what they do is allow the thousands and thousands or millions of volts that's on a power line. And that's what brings it from that thousands of volts down to 120, 240 that comes into your house. We don't want thousands of volts in the house. We want it brought down to a safe level so that if you plug something in, it doesn't equal instant death. Or very high chance of electrocution. This is what allows that to happen. And that's what's called a transformer. It brings down the voltage from high levels to low levels, or it can bring it from low levels to high levels, depending upon which way you're going with this. The other way this is used is over long distances. These are used to push the voltage up so that it can continue going down the road, or going down the line, as you should probably say. So think about this as, we go back to our river analogy, these are tributaries that are feeding this thing, okay? They're allowing extra boost of water so that all the water continues making its way downstream, okay? Easiest way I can say that is that these guys are just the boosters, or they're the side streams that are pulling the water away, okay? So they're either putting water into the stream or they're pulling it away. But when it pulls it away, it pulls it in such a manner so that it's not overpowering the whole stream, and you're not ending up with a flood downstream of that one, of that little offshoot. These are some semiconductors. You have integrated circuits and transistors and diodes. Diodes should sound familiar, because if you've ever heard the term LED, that stands for light emitting diodes. Diodes are a one-way gate. They're very useful in allowing flow of electricity in only one direction instead of two, which AC current, if you have not ever dealt with it, it flows in both directions. That's why it's called alternating current and not DC, which is direct current. We'll kind of get more into that as we go through this class and into the next one. Then you have transistors. Again, these kind of almost act like a one-way bridge. You get voltage out and current out at one end, but the rest of it just goes and feeds to it. And then you have integrated circuits. Integrated circuits are something you'll deal with if you do the class in digital or in solid state. These are very common in integrated circuits, and I'll kind of leave it at that for that one. So the next thing we need to talk about are electronic instruments, exactly what they are, what they do, and how we need to deal with them. So one of the things you do need to be kind of looking for when you're looking to start getting tools for this class and for future classes is looking to get a good meter. If you are going to take DC, you need to have a meter that can read milli and microamps. You need to be able to read millivolts. But you need to have a meter that is going to hold up under different conditions and depending upon what you're going to do in the future. Okay. When we're talking about meters, you're talking about something that's going to include these three types of meters. And sometimes even it'll take on even more jobs, but these are the three main ones. It'll read voltage, it'll read current, and it will read resistance. Best thing about it is that it also has the ability to, this thing's basically a calculating through its own subset of calculations what these are. And it gives you a way of looking at voltage, current, or resistance relative to what it is able to deal with. And we'll talk more about that another day when we actually do something like a meter certification. So these three are all part of multimeters. You can get individual voltmeters, ammeters, and ohm meters, but you more typically will see them as multimeters just because that's kind of how they run. Power supplies, basically your computer won't work without that. Power supplies are what supplies powers and brings it from an AC voltage to a DC voltage. If you're looking at your computer, it's the little black box that is connected to your voltage source so that your computer is not feeding off of AC voltage, it feeds off of DC voltage. It basically is able to take AC voltage and convert it, or it can actually supply its own version of DC voltage or AC voltage depending upon your needs and uses. Oscilloscopes, these are more typically used for AC applications because they are able to take a look at what we call sine waves or different kinds of signals. You'll see them used in things like digital electronics and in solid state, whereby you're looking for a signal that's varying and may or may not be conditional. This is a power supply. Again, this thing's able to take AC voltage, turn it to DC voltage. There's some that you can actually use to get different kinds of other voltages at the other end. This is very commonly used with computers and other electronics so that we're not using AC voltages on something that is delicate. This is a manual ranging digital multimeter. So if you look, you've got your resistance in ohms. You have your voltage DC, you have your voltage AC, current AC, current DC. This one's able to check batteries like a 9-volt battery or a 15-volt battery like a car. It's able to look at frequency. But the thing you kind of need to look at is down here at the very bottom, and that's where your leads go in. So this one is good for voltage and frequency and resistance. I'm sorry, this one's just for voltage and frequency if you look at this one. This is your common, this is where you would look at your current and your resistance, as well as being able to, I believe that's for checking fuses. And then you have just your basic high current port. It's actually fairly common. This one's an auto ranging. So this one can read current DC, current AC. This reads continuity and diodes, resistance, millivolts, volts DC, volts AC. And again, if you look over here, you can see where your leads go in. This guy reads 10 amps. This will read up to 300 milliamps. This guy reads voltage, diodes, and resistance, and this is your common lead. But what you will should notice is the fact that this does not lend itself to reading milli or microamps. This just basically will read amps DC and amps AC. When you start trying to read something smaller with that, it might not read true, or it might read kind of weird. That's the way I can put that. This is an oscilloscope. So what you would see if you turn this on, if you look at it for DC, I'm sorry, I cannot draw. What you should see for DC is a single straight line. You have to excuse me, I can't really draw with a mouse. If you were looking at a signal for AC, however, what you should see would be a sine wave. And the way you would clarify it is using these different dials to kind of dial in on what you're trying to look at and how you want it to be viewed. It's something, like I said, you'll use heavily in AC. All right, so it's kind of as a review, you have three basic things that allow you to look, you have four different mathematical uses here. You have voltage, which is the difference in electrical potential that allows for current flow. It's the push of the river. It's what feeds it and makes everything move. You have current, which is the flow of electrons. So one of the big things you have to make sure you don't do is mix that up with the flow of protons, because technically forcing protons out of an atom is extremely hard. It takes particle acceleration, and it's not something generally done. What you're making move is not protons, it's electrons, guys. Again, that's something I've commonly heard, is that people always try and tell me it's protons moving, that we have a positive flow. No, you're moving electrons, guys, so make sure you have that firmly affixed in your mind. Resistance is the opposition to flow. Basically, it's what's trying to keep everything from moving downstream at a pace that would cause havoc otherwise. And then to produce power or work, you have to have all four of these. Basically, all of this has to work together to produce power and to produce any kind of work. Easiest way I can say that, guys. So some things to know from this, and you can always go back and re-listen to this. I'll have this out on the YouTube channel, or you can click back into this at another day. But you need to know resistance and what it does. Dissipation, that is again where heat is dissipated through resistance and current coming together. Your different types of resistors, excuse me. So that's your potentiometer, your rheostat, your thermistor, your photoconductive cell, your basic resistor, things like that. How to do 3, 4, and 5 band color codes. I will have worksheets out there for y'all to look at, and we will work on some of those in class. You need to know what power is and how to calculate it, as well as voltage, current, and resistance. You need to know what a DMM stands for, which is a digital multimeter, and the difference between a rheostat and a potentiometer. And that is all for this.